And my talk today actually does sort of bring together several different themes of my career. I am a basic scientist, earth scientist. I'm interested in fundamental discoveries and things like that. But I've worked with industry a lot, and I found that actually really stimulating, and it's actually sparked a lot of discoveries that I've been involved in. And today I want to talk about something that we've done over the last 5 years. The last 9 years I've been living in Taipei. I've been at National Taiwan University, and then actually Jonny Wu and I and our group actually developed what is really kind of a startup field there that I'm very excited about. I think there's, my son actually does startups, and startups really involve seeing some need or seeing some opportunity, and then figuring out which ones can we actually bring about in some creative way. And so I want to share some of this with you, and maybe even to step back, that in science, if you think about how science has changed, since I was a student, or since my professor John Rogers was a student, these fields of earth science change enormously. They're like a box that are always changing their contents, and these contents are sort of new industries, subdisciplines, and things like that start up. And I think it's very important to develop new industries. And that's what really gives the students new opportunities and things like that. And it gives exciting careers for all of us. And so let me share some of this with you. And then actually Huawei was talked me into coming to University of Houston with Jonny Wu, the last 5 years we've been developing this field. Jonny is sitting back here, and Iwei, who got the poster award, but had to go back to class. He's his student. And well, all of you know something about plate tectonics. It's hard to avoid that, but the plate tectonic revolution really started when I was a student, and it was really based upon marine magnetic anomalies and things like that in the ocean. They were actually being recorded really for military purposes. There were people concerned about finding nuclear submarines of the Russians and things like that. And by now, plate tectonics is very precise. We know the motions of the surface of the Earth from these kinds of data quite well. But there's one problem with this plate tectonic revolution, and it's fairly obvious. Once you take these precise reconstructions based upon the seafloor and move them back in time, very quickly you find that, well, there's actually enormous parts of the Earth that have been lost to subduction. And so this is really reconstructing the convergent areas of plate tectonics is something we're still not very good at, and we're really data starved. Now many of us who are geologists have spent a lot of time on the margins, the mountain belts on the margins, and you can find pieces of oceanic crust, ophiolites. You can look at the stratigraphy that's been displaced thousands of kilometers, and you can start to develop theories of what went on, for example, in the Tethyan Ocean here. And so and these reconstructions can be important in petroleum exploration. But here are some, I think this is in the Campanian, a reconstruction of part of Tethys. And if you look at this, there are certain things like Semal and Shayak and Spongtang. Those are ophiolites that are found in Iran or in the Oman Mountains or in the Himalayas. And, but the details of these reconstructions of these ocean basins are actually very tentative in many ways. And so here's the first half of the plate tectonic revolution based upon these magnetic anomalies and hotspots. You end up with parts of the Earth that we have extremely high confidence in these reconstructions. This is 80 million years. But then you go to the opposite side and you have all of this gray matter that is terra incognita, and we want to deal with this. And I want to actually use an example from East Asia for quite a bit of this. And this is the Philippine Sea plate of the East Asia at 80 million years. It's just a little dot someplace in terra incognita. We don't know where it is, actually. But so that's the situation with plate tectonics. But the idea that we gradually started to get, actually working in Taiwan, there was local tomography. I'll show you some of the local tomography. This is something, what I'm talking about, I think we can apply at every scale, all the way down to the reservoir scale, to solve problems. But starting in Taiwan, we worked on local tomography in this amazing arc-continent collision that's very famous now in the world. It's like the Alps, forming offshore of Houston, and there's good tomography. We started to trace downwards, and we start to find, well, here's the subducted lithosphere of this arc-continent collision, and then there's other lithosphere down here, and this is the Pacific subducting down here. And so we started to get the idea we could actually take these tomographic images that these seismologists have been developing to higher and higher levels, and we could actually do something with that in some quantitative way. Now, the problem with understanding the tectonics of this part of the world, or all of Southeast Asia, is you have things like the Philippine Sea plate here that is almost completely surrounded by subduction zones. So it's very difficult to know the past motions of this plate. Now, we know something about the present motions of the Philippine Sea plate. These are the motions relative to Eurasia. Here, again, is Taiwan, and the Marianas are here. And basically, it's moving super fast. It's moving towards the west at about 10 centimeters a year, which is much faster than it can actually move by its own subduction zones. It's actually being pushed by the Pacific, and it's almost moving with it down here. It's almost locked to the Pacific there. But we can show that that's not typical of its past motions, because people have done a lot of paleomagnetism, and this is actually very messy and complicated, but basically it's well understood that over the last 40 million years or so, since the Eocene, it's moved northwards by about 20 degrees. That is, it's moved northward from the equator there. And there are a lot of different ideas about exactly how it moved, but so let's take this out, take out this is another one of these movies going backwards in time. This is the Philippine Sea plate. It's moving backwards. It's actually rotating. There's some evidence from the paleomagnetism for a lot of rotation, maybe even 90 degrees of rotation. And then you get back to the Eocene, 52 million years, and it's near the equator, but there's actually no paleomagnetic data at this time. You have to get to about 40 million years before you have any data. So, but we don't know the latitude at all. So this is just to show again what's the problem with plate tectonics in all these subducting parts of the world. Now, what I want to do is actually to fill all this gray area with plates, and we're going to look and try to find them in the mantle, map them out using really just petroleum exploration mapping technology, restoration technology. We unfold these things and we bring them to the surface of the Earth, and we found that we can actually fill this space. And so that's what I want to do fairly quickly, take you through this. And so we've developed some workflows. I won't talk about them in detail, but we map data of various sorts, especially tomography, but also seismicity and other kinds of data. And we have several different ways of unfolding them. I'll illustrate a couple of those. And then we bring these into plate tectonic software. So that's pretty much the workflow. Now, in the petroleum environment, you're just dealing with things that are fairly small regions near the surface of the Earth, so you can use an orthogonal framework. So that's the typical framework. We actually do all of this in GoCAD, Earth modeling software. But when you're dealing with the Earth and you're going halfway towards the center of the Earth, then this is really actually a distorted environment there. But we can easily map within this distorted environment, but then we take everything into a spherical environment. So within the GoCAD orthogonal environment, we just build a sphere in there, and so we can move things in and out of the spherical coordinate frame, and we have various little tools for doing things like that. So that's roughly what we do. So it's pretty much petroleum structural geology, I'll tell you. In fact, some of the tools that we use we developed, actually I was involved with Chevron early on in GoCAD, and we were concerned about unfolding stratigraphic reservoir horizons. And some of that technology is now well established and this is actually a map of the Sunda slab going from near Sumatra all the way over to Borneo and the Banda Sea there. So this is maybe 5,000 kilometers or something like that. And this is in a spherical Earth view here. We're looking towards the south. And then what we do is we actually just unfold this to a tangent plane, because that's what you can do in GoCAD or any unfolding software. You unfold to a horizontal surface. So, and then we just map this back onto the surface using a Lambert projection, something like that doesn't have much of any distortion. But you'll notice here that the changing area of the slab by the time you unfold it and get it back on the surface of the Earth is about 0.5%, something like that. This is an unfolding algorithm that presumes that folding is just a developable surface, like having a piece of paper you just flex. So slabs in the upper mantle, where you have this huge viscosity contrast between the asthenosphere and the lithosphere, actually do approximate developable surfaces very commonly there. And so you can just flexurally unfold them. And here it is at the surface of the Earth, and then you can take that and just use that in plate tectonics there. Okay, so then I want to illustrate this with Southeast Asia, particularly the Philippine Sea plate. This is actually a part of the world that's imaged very well. There's huge numbers of earthquakes and lots of seismometers, especially in mainland China and Taiwan and in Japan. Also Australia, and so these are just some checkerboard tests. But this region is pretty well imaged, even though the resolution of the tomography is not very high. But it's big enough if you're dealing with plates that are 5,000 kilometers across or something like that. It's good enough resolution to do it. So what do? We map. This is just an example of the Ryukyu slab. This is at the northern edge of the Philippine Sea plate. It's subducting in the region between Tokyo and Taiwan, and it comes down and actually lands on top of the Pacific plate. These are both flat slabs down here. But the way you would map that is, there's also earthquakes here. You might just map where do you think that the middle of that slab might be. And somebody else in the group might have a different opinion about that, but we all map it and we sort of come to some consensus on that. And we slice in many different ways, and you end up with a whole bunch of these lines, a whole mesh of those, and then you just form that into a surface there. So this is pretty much just like mapping any seismic, you know. And so we make a T-surf out of this, a triangulated surface, and then at each node in that we can store all kinds of information like the seismic velocities and the current depths and what the Gaussian curvature of it is and lots of different things like that. And then we can unfold this, and so here it is, that slab is unfolded. And so we restored part of the Philippine Sea plate here. And then we can bring it into plate tectonic software, this G-plate software. And we were looking at this slab, but there's some other little pieces that fit together, and there's another piece down here. And so this is the present size of the Philippine Sea plate, including the subducted parts of it. And then we can, if we're going to, basically this is going to be a piece in a picture puzzle, and it's going to fit together with other pieces. But this piece is going to be changing size and shape with time. And so we can do that in G-plates. And so here is this piece moving forward in time and coming up towards having its present size. And so we can actually take that and we use that in our moving picture puzzle problem that we're basically trying to solve there. Okay, so but this is just these flexurally unfolded plates, and a lot of plates are actually more deformed than this. Now, before I started this, I saw mantle dynamics calculations that made the mantle look like a lava lamp or something like that, where everything gets stirred up or anything like that. But once we started to map these things, we realized that was actually crazy. It's not crazy, it was just an artifact that these models couldn't accommodate very large viscosity contrast, basically. And people are doing things that are more realistic now, but it is known that when you have a stationary subduction zone and the plate just goes straight down, like at the Marianas, when it hits the transition zone, you have this huge change in viscosity, and you get a lot of buckling of the slab and a lot of also plastic flow. And so here the Mariana slab comes down, and by the time you get to, say, 1,000 kilometers here, it's about 500 kilometers wide. So that's like 5 lithospheres wide there. So you have a lot of deformation. But that's something that a structural geologist can handle very easily. You just estimate the area of that with some uncertainties, and then you unfold it. And you take out the density changes and all of that. And you know, actually in the case of the Marianas, what is the rate of motion of the Pacific, and it's basically moving to this stationary subduction spot. And then you can, you know all that motion, and you can, well, first of all, you can figure out how long this was, and then I'll show you in the next slide how long. When you do that, you find out that there's 3,800 kilometers is subducted there, and it started subduction. The age of the bottom is 50 million years. So you can do that kind of thing. And that's actually very useful information, particularly if you do this in a number of different places. So Jonny Wu's done this, and some other people in the group have done this. And so if you go farther north through Tokyo, then you see the Pacific comes down and doesn't dive straight down. It actually lies along the transition zone, but also thickens up to here like it's 4 slabs, 4 lithospheres thick there. It's enormous. So once again, you just measure the areas, and you know how fast the Pacific is moving material into here, and you can, it's a trivial problem, and you find out, well, this started to subduct at 50 million years ago. And so you start to get the same number within the uncertainty, but in this case it's about 5,000 kilometers long, because you're in a different position and you're actually dealing with a different plate boundary in this area. Okay, so at any rate, so you start to do this and in different places, and so you have all of these pieces of plate that are like spaghetti that you've unfolded here. And at 50 million years, they actually fit. When you move the Pacific plate away, you know, we know the motion of the Pacific plate back to this time, and it actually fits pretty well against the edge of Asia there. But then as you go farther south, you're going out into this unknown land there. And if you go, so you can estimate, well, this is that Pacific slab, and so the bottom of the slab must represent some plate reorganization event. That's when you started to subduct. Well, it turns out plate reorganization events are nice because that's when all the pieces actually will fit together in a picture puzzle at the surface of the Earth. Okay, so I first show you the Marianas, so they unfold right here, and then you can start to see, well, the edge of the Pacific subduction went along Asia, but then went out into the Pacific here. Well, that's exactly what it's doing today as well. With now the Philippine Sea plate is here, and this is heading down to New Zealand. And in fact, if we do this all the way down to New Zealand, which is what we've done, and actually Iway, who got the prize today, has also done this up in Alaska and so forth, you find out it's 52 million years, plus or minus 10 million years, all the way down between New Zealand and Alaska. That's like halfway around the Earth. That all started to subduct at approximately the same time, according to this very simple unfolding of the seismic tomography. And then here's the Sunda slab unfolded. There's some other areas around that become the Himalayas that are not shown here. And then there's this big gray area. And so this should be where it's subducted. And in fact, if you look at different seismic tomographies, these are horizontal slices in different tomographies down at around 1,000 kilometers. We've been using this MIT tomography, but there's some Lawrence Livermore tomography. You can see there's, at that depth, we're looking at the bottom, near the bottom of the slab. You can see essentially from New Zealand all the way to close to Tokyo, you have a continuous subduction or continuous slab at that depth. And that's actually right at the spot where the unfolded slabs fit to. So it looks pretty good that we can find this. And then, okay, so we're starting to develop some picture puzzle. We're starting to fill space. We have less of the gray area that we haven't dealt with. But then here's this enormous hole going from near New Zealand up to Japan and Hainan and so forth. And this is about 8,000 by 3,000 kilometers, something like that. It's an enormous thing. And what do we fill the hole with? We have to find a piece that's going to fit into there. And that's precisely what we're going to do. And so Jonny Wu was mapping this, and will show you. I know most of you can probably not even see this, but along this slice here, there's a seismic tomography from down near Tonga up to Tokyo, and there's actually a set of flat slabs in the upper part of the lower mantle going through this whole region. It's not absolutely continuous. There's actually several different slabs in here. But when you map these things out and put them in, actually this is the seismic tomography down at around 1,000 kilometers, but Jonny has called these the East Asian Seas, and these are several different things. There's also the Proto-South China Sea. These are the oceans that existed before the present South China Sea. And they're all at about the same depths, which represents pretty much the same time. Okay, so they basically fill this, most of this space, but not all of it. There are two major holes here. These minor holes we're not too worried about. We actually have many different little slabs as well, and we may miss some things and so forth, but it's to first order, we basically can fill that except for these two holes. And so we can't have any big holes in the lithosphere. We have to fill it with something. And those two gaps. Well, in fact, we have to put the Philippine Sea Plate there because there is a Mesozoic core that is a pre-52 million year part of is like kind of the seed of the Philippine Sea Plate. And because we have two holes, we have two different places we could put it, and so we get two classes of solutions, and we can perturb those solutions as well. But basically, those are the two solutions. But I'll just show you the preferred one, which by a number of tests is actually pretty clearly the correct one. But we end up putting it, we already know it's near the equator from the paleomagnetism. And then in the seed area of the Philippine Sea Plate, we know that there was a plume or a hot spot there. There was a hotspot track, but nobody knew really where it formed. But it turns out when you put it in this hole, it's right over the Manus plume, which is a present plume that has been imaged recently down to the core mantle boundary. And so that makes a lot of sense to have it right there. And then we have something called the Molucca Sea slab. This is the minimum size of it, but it has a lot of properties that make it seem that it's actually part of the Sunda slab or part of the Indian Ocean. In fact, these two slabs are actually touching each other in the mantle today. So this is our preferred model for this, and then yeah. So this is a movie. I'm going to show you a movie, and I'm going to show you it several times of this. And so we're starting at 52 million years, and you'll see the Philippine Sea Plate grow progressively. I showed you earlier that we worked out the progressive change in size of this piece. And so here it is moving along, and the red stuff that's here are actually the hotspot track there and it's by this time it's moved off the Manus plume. There's another Caroline plume that is forming over here, and it's rotating, and then it's actually starting to collide with Asia. The pink part is the Philippine Sea Plate that's being subducted, and then finally we're to the present. Now let me show you that again, because there's actually a lot of interesting things, and if you're interested in this part of the world, there are amazing phenomena that come out of this, and I'm only going to focus on a few things today, but one of them is that there's a collision between Asia, between Japan and near Taiwan, and the Philippine Sea Plate. So you have these two things coming together, and so you should have a mountain belt there. And people had not been predicting a mountain belt there. And I'll show you a little bit of the evidence for that in a second. Another thing that's kind of interesting detail is that we start to form a tear between the Pacific, this is Pacific Plate, and it's running over the East Asian Sea. And when that tear hits the continent, then suddenly you open the South China Sea there. And so the opening of the South China Sea is very much connected to this plate tectonics. Of course, in the petroleum industry and in the geopolitics of Southeast Asia, that South China Sea is very important, as we all know. So those are a few features right there that show up. There's another feature about this model. There's several different. There's the the collision between these two arcs. There's also collisions between arcs along the Pacific side that I didn't really point out. But there are arcs that disappear, and so if a lot of geologists, tectonic geologists, felt, well, if there's something that existed in this ocean basin as big as an arc, a plate boundary, we should see it in the mountain belt. We should see it in the Himalayas and things like that. But what we're finding is a lot of these things just go straight down, and there's no trace of them whatsoever. Because if you have the arc, it's between two other arcs, or two other plates, it just disappears and goes down with it. And you might get a few fragments, but we're finding that it's commonly not. So just the last little bits of this thing moving northwards is just the detail. This is the Philippine Sea plate. It's run over this tear, and so it's actually running over the Pacific now, and it's actually producing a flat slab in the mantle there. And then it's about to collide probably around 17 million years ago. And then we predict that there should be a mountain belt in here. And we also predict there should be sediment that come off of this, and actually in the Philippine Sea plate, in ocean drilling, they do see that. And these would be actually big submarine fans. This would be like 1,000 kilometers or something like that. And then they show up there. And then also just like the South China Sea opens up when this plate transition comes into here, when this comes in here, the Japan Sea actually opens very suddenly, or at least most of its opening comes very suddenly. And there's a lot of magmatism when this hot region of the Philippine Sea plate comes in under Japan. So, just mapping out the tomography gives you a lot of insight and surprises. Now here's just a little bit from the literature going into the East China Sea. There's actually a number of places where they have a folding in the Miocene and then a mid-Miocene unconformity. And that's exactly the time of this collision. So it's actually very widespread in this part of the world. It involves inversion of a lot of rift basins. I'll actually show you those rift basins later in the talk. Okay, so so this is just fairly quickly going through this, and if you want to read the paper on it, it's in Journal of Geophysical Research. Jonny Wu's the first author, and it's open access, and it's actually book length. It's a giant thing. This is such a big and complicated part of the world, and we show how you do this, how you play this game, so you can go read all about it if you want. But we're actually now, we've been working all around the world, and we've actually by now mapped, I think, probably 75% of the mantle of the Earth in this. And mapping the mantle doesn't, this is a first cut out, but mapping the mantle doesn't actually solve all the plate tectonics. The plate tectonics is much more complicated to do because you have to integrate with all of the geology. You can't just do it with these pieces. You actually have to know the geology of all the surroundings. You have to really get the information from all these little fragments. You've got to have the paleomagnetism to know what latitudes these things might be at. This allows you to sort out all the different possible solutions. And so that many people, Iwei is shown here, who won the prize today, and there's Jonny and me with our red and green glasses, which we don't use actually at our work. But now here's a map. I just want to show you this map. This is just a hint of the future, and I'm going to stop and talk about something else for a little bit to just end up. But this is a map of that Jonny made, a year and a half ago, And these are actually just lower mantle slabs. And most of these are flat slabs. That's why you actually see them here. And the areas under North America, North and South America are not mapped very much, but we've been doing a lot of that more recently. Now, this just shows the present day geography. But if you go back to 180 million years ago, and I think I'll just jump there, and I'm sorry it doesn't really show Asia very well here, but basically you'll see that all of these slabs are now ringing around the supercontinent. They're filling the Tethyan Ocean, coming in around here, coming around Australia, Antarctica, South America here. And when you actually do North America, but wasn't on this, it actually keeps on going around to Kamchatka there. So we're actually finding that all of these slabs are actually surrounding the supercontinent. And that, by implication, is really that we're finding the oceans that existed around the supercontinent. That doesn't mean that we've worked out all the plate tectonics of them, but that suggests that these slabs actually go down to 2,500 kilometers or so. They don't get to the core mantle boundary yet, but it suggests that we have a history of plate tectonics that we can extract from the mantle going back to something on the order of 200, 250 million years, I think. I even expect on the core mantle boundary that we have plates that we can decipher, actually. So that's one of the things what we're trying to do. With the help of University of Houston, we're trying to start a center for tomography and tectonics and tomography, and this is one of our goals, is to really push ahead with this. But it's a big thing to do, and really there'll be people around the world working on things like this. But the opportunities are not just in plate tectonics, I would say. Though I would say once you do something like figure out the Philippine Sea plate, it suggests all kinds of other research that needs to be done in Southeast Asia, because it has so many implications that it generates a lot of excitement and new activity and new discoveries of various sorts. And so it's really it's a big opportunity for tectonics, and I think it has a lot of applications in exploration and at some scales probably for development as well. Now I just want to go into Taiwan now, and this is just a very simple slice in the global tomography with the Eurasian slab. It's basically South China Sea that's subducting under Taiwan, and then there's some local tomography that you can't even see very well. But right in the upper 100 kilometers or so, there's actually exquisite tomography under Taiwan because you have so many earthquakes and so many seismometers in the region. And and Taiwan has become a famous place. It's like the Alps, but it's going on super fast. The plate convergence is 9 centimeters a year, has one of the highest erosion rates in the world. So it's a very fast mountain belt. And it's right about in here, and you have the South China Sea is subducting eastward up to Taiwan, and then from Taiwan over to Japan, the Philippine Sea is subducting under Asia. So somehow you're flipping subduction as part of this arc-continent collision. And so we need to actually try to see if we can map this in more detail. I'm not going to show you in a lot of detail today because I don't have much time, but basically we map slabs not just by the velocities or by the colors here, but by the gradients there. And so here, for example, if you just look at the contours, the gradients here, the edge of the slab, the bottom of the Eurasian slab, actually goes all the way up to the coast of China, way north of Taiwan. I never expected that at all. It was pretty crazy. And so if you, but actually we see that because there's all this hot material under South China that is actually wrapping around the edge of the slab. That's what allows us to see that. So now we find it's actually quite consistent through depth that the slab goes way north here, and then here's the Philippine Sea slab going under here, there. So you can map these out, and if you actually look at these differences in velocity here, it's actually telling you what's subducted continental mantle lithosphere, what's oceanic mantle lithosphere, what's stretched continent of the South China Sea, and so you can actually sort it all out when you unfold that thing. But we can, so here is just looking towards Taiwan from Japan, And then that's that subducted, the two different subducted slabs, and that's the northern edge of it. And so we now know what's going on. There's no slab break-off. A lot of people think you collide the continents and you break off the slab. It doesn't break at all. It's actually a completely stable process of colliding, and it's just tearing as it goes along. The mountain belt is kind of like a wave crashing on the beach. You have a wave front coming in here. The beach is going like this, and it's oblique, and so the locus of active wave breaking moves along the beach, and then the dead mountain belt that's left behind, which is called the Taiwan Sea Belt, which is along in here, it's just the high water mark of the wave there, and it has super simple kinematics there. But we never knew how that was working in 3D before we had the tomography. Let's switch to a different thing. Here's a section through Taiwan at much more higher resolution. This is just 10 kilometers down here. There's some oil wells actually on this section here. And this is the mountain belt right here. And these are the metamorphic rocks of the mountain belt. But we actually see sediments going in under the mountain belts, rift basins and things like that. And it's quite obvious you start to map out this tomography. So we didn't know that we had these deep rift basins. We knew we had some normal faults that had clipped off some sediments in the thrust sheets. But basically we find, here's the mountain belts out in front, the basins out in front of the mountain belt, the 4 deep basins. There's some rift basins in the Eocene, but then this is the shelf edge of the South China Sea, and then you have the very thick continental margin sediments, and they actually go in to southern Taiwan here. It's called the Tainan Basin, but in the tomography we see that the shelf edge keeps going across underneath the mountains, and we have the deep basin with the sediments are actually 23 kilometers thick there, and they go completely under the mountain belt there. But we also find these basins that I showed you in the earlier cross-section. These are the rift basins. They're north-south basins, and they run through this whole region. All just a big surprise. And so some of these things might even be, there are some predictions that they might influence the fluid flow in the mountain belt, actually, in the foreland. So here are some of these basins here in S and P and P to S ratio, and you can actually show that these are quartz-rich sediments there. The continental margin down here isn't quartz-rich, but it's overpressured, you can show from the velocity analysis. And actually, in the mountain belt of Taiwan, we have rocks that are also extremely quartz-rich, and that's probably the sorts of basins we're seeing. These are Oligocene and Eocene rift basins. So these would be some that had been taken off by thrust sheets. I'm almost to the end here, but so these basins, here's Taiwan right here, here's the South China Sea, and then this is the East Asian Sea, or the East China Sea, and these are these big rift basins and smaller rift basins of the East China Sea, and they're basically the same age, apparently, as these rift basins that are under Taiwan. These are also reactivated in post-Oligocene, but we know these ones under Taiwan are as well. So we can start, even with tomography, we start to get some things that may be of some interest for understanding the regional development of this area of petroleum exploration there. Now these basins under Taiwan actually go much deeper. They get down to 35 kilometers. That's because they're subducting now. That's not their original depth there. And also, you may be aware in many continental margins you have shelf edge magnetic anomalies that run along them. The east coast of the United States has that, and there is one in the South China Sea going from essentially Hong Kong over to Taiwan. And it's interesting to see that it terminates under Taiwan. And what we do, when I mapped out these rift basins, I found that, well, it's actually clipped off by the rift basins there. There's a tremendous correlation between these rift basins and these magnetic anomalies here. And so these can't be just simple rift basins. They have to have a lot of transtension to them, would probably strike slip faults, transform zones that have some rifting along them. And so these are just a few little surprises, just little examples of the richness of the kinds of data that can be brought to bear, but especially focusing on the tomography, which is something that we haven't worked on, people haven't worked on so much scientifically, and I think it's at all of these different scales, it's a big opportunity. And am I out of time? Did I talk too long?
You're okay.
I'm okay, because I'm almost to the end. One other little tidbit here. This is Taiwan here, and this is the Luzon Arc, and so we're just seeing the beginning of this oblique collision there. And so what is the accretionary wedge rises up above sea level to be this mountain belt that goes up to 5 or 4 kilometers high under Taiwan. But what happens? Here's the volcanic arc coming up here. And then this other red line is the edge of the former edge of the Philippine Sea Plate, it's the forearc here, and the whole forearc collapses. It's the arc that's colliding, and its forearc basin just collapses, and it's about 100 kilometers wide before the collision. It's about 5 kilometers wide afterwards. There in map view. Okay, so what happens? So we've lost a lot of the Philippine Sea Plate. But it's the Eurasian plates that's subducting. So where's the Philippine Sea Plate? And we actually, now when we go to, say, offshore of eastern Taiwan, I have a student in Taiwan who's actually reprocessing all the seismic lines, and we find that there's actually big flat thrust sheets there. And this one has about 20 kilometers of slip. And it steps down, it's on the Philippine Sea Plate at the base of the pelagic sediments, and it's about 6 kilometers below sea level there. It's about 5 kilometers of sediments there. And so we have thin-skin tectonics. Now, actually, when you go on shore to where the arc is exposed, you also have thrust going the opposite direction, but they also go down to about 5 kilometers. And it's also thin-skin tectonics. Now, if you have thin-skin tectonics, that means you have subduction, if it's tectonics. If it's gravity slides, like the Niger Delta, that's a different story. But if it's tectonics, that tells you that you've subducted, and these are all rocks that are part of the Philippine Sea Plate. So you have to have subduction of the Philippine Sea Plate. In that earlier map, I didn't tell you how much it was, but it's about, all of this is about 120 kilometers of shortening in this. And so you've, here's 120 kilometers of shortening. So where's that lithosphere? Okay, well, let's see. This is a slice through tomography down at 35 kilometers. And this is the outline of Taiwan. This is the base of the crust, the Eurasian crust under Taiwan. And then there's some other lithosphere in here, and it's only about 30 kilometers wide. It's a thin thing, but it's actually mantle and crust of the Philippine Sea Plate. There, it's of the leading edge of the Philippine Sea Plate, has disappeared there. And then here, this is actually, this is VS and VP here. We see it in both of them. And then this is the kind of funny subduction systems in here. But so we have an extra subduction that's going on here. Both plates are subducting, and they're both subducting in the same polarity there. So I'll just sort of end with this last one, but these are the two thin-skin systems on both sides of the mountain belt associated with the two different plates are subducting. But this piece in here is basically the leading edge of the Philippine Sea Plate, and it's been clipped off, and it's subducting. It's almost done subducting, but it's actually taking up 2/3 of the 9 kilometers of plate, 9 centimeters a year plate convergence. And the Philippine Sea Plate, or Eurasia, is only taking up 1/3 of that. And so it's actually super important. So I think it might be actually something that would be very common in many mountain belts. If you took a cross-section of the Alps, you have this same reversal polarity as you go. This could be the Po plane, and it means you have to be actually subducting Adria plate as well. You can't be just subducting Eurasia under the
Thank you.
HGS also has a speaker award for Mr. Suppe.
Oh, wow.
It's a piece of rattlesnake limestone.
Wow. This is... Is this a reservoir rock?
It looks like it.
Yes. Reservoir rock.
It looks like some Paul. Do you want to talk about closing?
Oh,
Close anything?
Oh, here.